Okay, let's say we have samples of a random variable or a random quantity. To have an idea about the typical behavior of this quantity, what we usually do is look at the average. And when we say average, there are actually three types of average we can talk about. Suppose that we roll a die 9 times and the outcomes are this: 2, 3, 3, 1, 4, 3, 6, 5, 4. Okay. Now, first of all, you can add all these up and divide by 9 number of the outcomes to obtain what we call the sample mean. Okay, so that is 3.444, etc. And this is the sample mean. This is essentially the average of the outcomes. And it tells you something. On the average, you have this value. Or you can maybe look at the middle value after you sort the outcomes. So 1, 2, 3, 3, 3, 4, 4, 5, 6. So what is at the middle point? 3 is at the middle point. So this tells you something else about the behavior of this random quantity. And this we call the median. The element at the middle we call median. And another one we can think of is called the mode. And that is the outcome that appears most often. Okay? So here you have 3 as your mode because it appears 3 times, and 1, 2, 5, and 6 appears once, 4 appears twice. So 3 is the mode of this sequence. So for instance, as a different scenario, let's say we roll the die 10 times and the outcomes are this. And these are the same, the first 9, but I have another 4 at the end. Now my sample mean is, again, add them all up, divide by not 9, obviously, but 10. And the result would be 3.5. Again, for median, sort the values. But now, since I have 10 outcomes, there is not one single midpoint. I have 5 here and 5 here. So actually, this is the midpoint. So what you do is you take these two and take their average. 3 plus 4 over 2, you get 3.5. And finally, again, sort them and look at which values appear most often. So 3 appears 3 times and 4 appears 4 times. In this case, we say that this sequence is bimodal. Okay, you have 2 modes, 3 and 4. There might be more than 2 modes, in which case we will say that it is multimodal. But obviously, this is a very small sequence, and it doesn't carry much information. But in general, bimodal or multimodal distributions are important in some applications. Now, this is when you have data. When we go into the probability theory domain, what we are going to talk about is, rather than those, we are going to talk about moments, and first and foremost, the expected value or the mean value of a random variable. And for a discrete random variable, this is defined through this definition. Okay, the expected value, notated in this way, is equal to the sum of all outcomes, k, weighted by their assigned probabilities. So for instance, well, this is a weighted sum. Assume random variable x has this PMF, so the outcome of 1 has probability 1 over 4. The outcome 2 has probability 1 over 2. And the outcome 4 has probability 1 over 4. Therefore, you see, this is 0, 1, 2, 3, 4, 5. I have a probability of 1 over 4 at 1 and 1 over 4 at 4, and a probability of 1/2 at 2. And I'm going to take a weighted average of these possible outcomes. It's a little bit like a center of mass, if you like. So this point here is going to be the expected value, the weighted average of the outcome. So 1 is the possible outcome, 1 over 4 is its assigned probability, 2 is the possible outcome, 1 over 2 is its assigned probability, and 4 is the possible outcome, and 1/4 its probability. Add them together, you get 2.25. This is the expected value of this random variable. Now, the mean of a function of a random variable, a function of a random variable. Now, in this case, suppose that you have data. How would you do it? Let's say you have, let's go back to this example here. Let's say this is your data. If I ask you what is the expected value of the squares of your outcomes, what you would do was to obtain that is apply the function. So 4, 9, 9, 1, 16, 9, 36, 25, 16, 16. Then add them all up, divide by 10, and you get the answer. So what we are going to do is a little bit similar here. Instead of the indices here, the possible outcomes, we are going to apply the function g to the outcomes and then take the weighted sum according to their probabilities. It's the same procedure. And a direct consequence of this is the linearity of expectation. If you have a random variable x and apply a linear function to that in the form of ax plus b, where a and b are real numbers, what you get is equal to a times the expected value of x plus b. It's not that difficult to show this using the properties of addition. Essentially, that's what makes expectation linear, because its definition is in terms of sums. And the powers of the random variable x is called the moments of x to the power n. This you can see this as a function of the random variable x. So g of k equals k to the power n, if you will. And expected value of x to the power n can be found in this way. K to the power n multiplied by the assigned probability, add them up, you get the value. This we call moments of random variable x. And for instance, this is the second moment, this is the third moment, and in general, this is the nth moment.